Okay, gang, this is section 1.6, number 37. So we're going to graph this. So this is what we would call a piecewise graph. It's two or more graphs collaged together into one graph. The first column is the functions that we're going to collage together. And the last column is the domain restriction. So this last part tells us where we're going to turn the function on or off. Alright, so let me start with the first function. I'm going to draw the functions individually, and then I'll put together the final answer. Alright, so this is the first function they're using in this piecewise graph. I'm just going to rewrite this because this might be confusing to some people, the way this is formatted. So right away you should know, since it's an x squared, that it's a parabola. There's a negative in front of the parabola, which means it's a face down parabola. And remember, it's opposite of the inside, so the vertex is 1 unit to the right because that's the opposite of the inside, and 1 unit up. So the vertex on this parabola, opposite of the inside, same as the outside, is 1, 1. Okay, so that's the vertex and it's face down. I'm going to go ahead and find the x-intercepts for this by setting y equal to 0. Okay, so why don't we just go ahead and move this to the other side. Okay, and I'll take the square, I'm going to do the square root method. So that means I'm going to take the square root of each side, and then just don't forget your plus or minus. Hopefully you guys remember the square root method from pre-calc. Right now I'm going to move this 1 over. So x is going to equal to 1 plus 1, which is 2, and 1 minus 1, which is 0. So the two answers are 2, 0, and 0, 0, because we already started with knowing that y was 0. And I won't go find the y-intercept because the y-intercept is going to be the same point here, because it's going through the origin. Alright, there's the first graph. Alright, now the next graph. This is a radical, so a square root looks like a hook. And remember, it's always the opposite of the inside. So if it's minus 2, it means it's 2 to the right. Now, I'm just going to put in some scalar points. So that means, like, if x is 3, 3 minus 2 is 1, square root of 1 is 1. So I'm just like plotting some points just so I can get like a little bit more information. Sorry, a better scaled graph. Okay, so like if I pick 6, 6 minus 2 is 4, square root of 4 is 2. So that's the point 6, 2. So remember, when you're graphing, the most important first step is to know the basic shape, what it looks like. And then you have to know, how does it move left, how does it move right. Remember, left, right is always the inside of the function, up, down is the outside of the function. Okay, so now let's talk about the restriction. So let's go over this part now. So x is less than or equal to 2 for this guy, and x is greater than 2 for this guy. Alright, so what you want to do is you want to actually cut it at 2. So, and it has the bar, so it's going to be closed when you cut it. So we're going to cut this function in half at 2. And we're going to take everything to the left, because they want things where x is less than 2. That's where the function is turned on, so to speak. So when I draw my final answer, I'm going to try to squeeze it here in the corner. You want to have all key values in your final graph, so that would be anything like a vertex, an intercept, a boundary value. A boundary value is where you cut it. So this at 2, this is a boundary value. Where we cut it. We cut it at 2, 0. That's the boundary value. Alright, so it's closed at 2, 0. Now I'm just going to carry these points just so I have it scaled nice. Oh, I put that guy in the wrong spot. Okay, so I'm just taking from this function when x is less than or equal to 2. So that's why you only see part of the graph. I'm not taking the whole graph. Alright, now from this guy, I'm cutting it at 2. So at 2 is here, and since it doesn't have the bar, you want to think of it as an open circle. And I'm taking everything to the right. Okay, so now this is important. If you have, see, you notice these are both at the same spot. The boundary value on this one is 2, 0 as well, except on this case it's open, where in this case it was closed. Okay, so they happen to sit at the same spot. So an open overlapping a closed is a closed. Think of it like snapping a button. A button like a snap, where it just snaps together. One side's open, one side's solid. It just snaps into a solid. Alright, now again, I'm just going to scale it again. Okay, so it's going to snap together here. Don't put an open around a closed. That doesn't make any sense. An open around a closed is closed. Okay, so this is the final answer here. This is what we're looking for. This is sort of like a collage. You're taking two different functions and making a new interesting function from them. Alright gang, that's the end of this video. Hope that helped. Bye-bye.